In this lesson, we are going to talk about the Gauss method to solve linear equation systems. We are going to see how these types of systems are resolved by using this method. And for that, you have to remember that it is a linear equation system, how the equivalent systems were passed. That is, systems that have exactly the same solution. And to finalize with the resolution, we can see how linear equations are resolved. So first, remember that a linear equation system is a set of equations that are all linear, such as the example you have on the screen. X plus 3 and minus z equals 2. 2x minus y equals minus 4. These types of systems have a solution or do not have it. Then solving the system implies finding all the possible solutions of the system, or deciding that it does not have a solution because there is no set of numbers x and z that meet both equations at the same time. So, what we are going to do with the Gauss method is try to find the general solution of the linear equation system. That is, all possible solutions, and classify the system according to the solutions that it has. If it has infinite solutions, it will be an indeterminate consistent system. If it has a single solution, it will be a consistent determined system. And if it does not have any solution, it would be an inconsistent system. Well, before applying the Gauss method, then notice that if I have a system of this style, 3x minus 2y equals 4, 2y equals 8, this system is very easy to solve. Since from the second equation, I clear the y, and I know that there is 4. And if I substitute this 4 in the first equation, I clear the x, and I get that in this case the x is also 4. These types of systems are very easy to solve even if they have more equations. If it is in that same way, notice an equation. Another equation, but the third one I can clear the z in this case would be 2. If I substitute this 2 here, I clear the y, and if I substitute the value of z and of y that I obtained in the first one, I get the x. In this case, z equals 2, y equals 7, and x equals 8. A system of this style is easy to solve. However, when I do not have the equations in this way, if I do not have more general things, 3x minus 2y and plus z equals 4, 2y and minus 3z equals 8, 3x minus 2 and plus z equals 6, then it is not so easy to solve, since I cannot in any of them clear one of the variables and substitute to obtain the specific values of each one of them. Well, Gauss method is going to consist in that, to take this system and try to transform it into an equivalent system that has this form of here, so that it is easy to solve. Gauss method, as I said, we are going to do it by equivalence transformations. That is, we will pass from the original system to a simpler equivalent system to solve using equivalence transformations that are allowed for the systems. And it is about getting zeros among the coefficients of the 5 unknowns. What equivalence transformations can we do? Well, if you remember, we can transform one or several equations into another or other equivalents. We can solve one equation of one of the 5 unknowns and substitute it in all the others. Or we can also add to an equation the result of multiplying another by a non-zero number. All these operations will allow us to pass from the original system to an equivalent system. That is, with the same solutions, but easier to solve. Well, we will start seeing how to apply Gauss method with examples. We will start with a consistent system. Let's see what happens with it. So the method that consists of taking the system, x plus 3 plus 4z equals 2, 2x minus and minus 2z equals 9, x plus 10 plus 12z equals 5, and applying equivalence transformations to transform it, doing zeros in some coefficients, for example, in this one and in this one and in this other one here, so that I only have the z and I can clear it. That is the idea. Well, how are we going to do it with equivalence operations? I take this one here and we are going to do one zero in this x and another zero in this x. As I can, to an equation, subtract the multiple from another. Whenever I multiply by a non-zero number, for example, the equation 2 minus 2 times the equation 1 makes 2 minus 2 disappear x minus and minus 6y. It gives me minus 7y, minus 2z, minus 8z. It gives me minus 10z, and 9 minus 4 gives me 5. The same for the third one. If the third one remains directly the first one, well, I get a 0 here and I get 7y plus 8z equals 3. As you can see, I already have two coefficients of the two coefficients of the x in the last two equations, nulls. If now we try to do 0, the coefficient of this I, so that only the z remains, well, we simply have to add the equations 2 and 3. The first remains as it is, the second also, and the third I add the second, so that the y disappears. This is already a system of the easy to solve. Z is worth minus 4. I substitute here the z. The y is worth 5. And I substitute above the value of the y of the z, and I have that the x is worth 3. A consistent system with a single solution. Well, this is the Gauss method. As you can see in the Gauss method, the only important thing in reality are the coefficients of the unknowns. We are going to apply the Gauss method again. We are going to do all this again, but with a different notation, with a notation as a number box, where only we are going to take into account the coefficients, because in reality they are the only ones that we manipulate. And so it is much easier to see what kind of operations we have to do. So for example, this same system that we have just solved, I can write it this way. If I take the equation 1 and I write coefficient of the x, coefficient of the I, coefficient of the z, and I end up independent after the vertical line. Equation 2, the same. Equation 3, the same, but taking care that the x goes below the x goes below the x, and the z goes below the z, because operations do not allow us to make calculations mixing variables. So what is the first operation that we have done? Well, if you remember, we have done a 0 here in this 2 and a 0 here in this one. What operations? Well, in equation 2 we have subtracted 2 times 1, and in equation 3 we have subtracted 1, so that we have obtained those two zeros. As you can see, here it looks much more visual than I have those two zeros there, really. Then, what operation have we done continuously to obtain a 0 here? Well, exactly the same. If in equation 3 I add 2, I obtain that 0 from there. So as you can see, we have made 0 below this line, 1 minus 7 minus 2. Once I have 0 below that line, these three zeros here, we transform it again into equations. This will be the equation 1, the new equation 1, the new equation 2, and the new equation 3 of the new system that is equivalent to the previous one. As you can see, x plus 3y and plus 4z equals 2, minus 7y and minus 10z equals 5, and minus 2z equals 8, a system equivalent to the previous one. As you can see, this way of working is much more visual than the previous one, and the result is exactly the same. We have obtained exactly the same equivalent system, from which we can clear the z, and obtain that z is worth minus 4, and y worth 5, and x equals 3. The result is exactly the same. As you can see, this way of working is much simpler. We are going to make zeros below this line, and it looks much more visual. Well, this is what happens for a determined consistent system. What happens if I have an indeterminate consistent system? Well, at first we know, but if we did not know, we would reach the conclusion that it is. So if I have this system, I do the same operation. Equation 1, 1, 2, minus 5, 4, only the coefficients, we remember. Equation 2, minus 2, 1, 0, because the z is not minus 3. And equation 3, 3 minus 2, 1, 4. And the same, we are going to do 0 below this line, below this one, below this one, and below this one. And that is the last one. Then we are going to try to do zeros in minus 2 and 3 and in minus 2, starting from this column. Well, the first operation that we do not occur directly from seeing this is, if I add this to minus 2 twice the 1, 2 times 1, it will give me 0. Well, equation 2 plus 2 times equation 1, minus 2 plus 2, 0, 1 plus 4, 5, and 0 minus 10, it gives me minus 10. And on the other side of the equality, minus 3 plus 8, 5. Here, also clearly, if I subtract to this 3, the first row times 3, well, I already have it, because equation 3 minus 3 times equation 1 gives me the other equation, and gives me a 0 here. Well, if we continue, now the next one is to do a 0 here, because it is below this line, the 1, 5, and 16. Well, we are going to do a 0 in that minus 8, but before, given that 5 minus 15, they are all multiples of 5, and minus 8, 16, and minus 8 are all multiples of 8. We can simplify the equations in this way. I can divide by 5 all the second equation, which gives me 1 minus 2 and 1. And I can divide by 8 all the third equation, which gives me minus 8, and so I have 1. 1 minus 2 and 1. As you can see, this way is simply to have smaller numbers, and that can be done because it is one of the operations of valid transformations, like equivalence transformation. Well, once I have it like this, it is very easy. To the third equation, I subtract the second, and I get the 0 here that I was looking for, and also in this case, I get all zeros. So once I get to have zeros below that diagonal, that is 0, 0, and 0, then I transform it into new equations. Equation 1, equation 2, and equation 3, they are the new equations of the new system. X plus 2y and minus 5z equals 4, and y minus 2z equals 1. And 0 equals 0 is not necessary to put it because it is an identity. Then I have achieved a system that is equivalent to the previous one. This system, already directly we solve it, giving parameter value y or z. We choose, for example, I have chosen z, and I say if z is a real number, then y is 1 plus 2 alpha, and substituting in the first one, x is 2 plus alpha. Then the solution, this system is an indeterminate consistent system with infinite solutions that depend on a parameter that has a degree of freedom, which is the alpha. If z is equal to alpha, y equals 1 plus 2 alpha, and x is equal to 2 plus alpha, for each one of the alpha values, it would have one of the particular solutions. Well, this is what happens for an indeterminate consistent system. What happens if the system is inconsistent? That is, it does not have a solution. Well, let's see what happens when applying the Gauss method. We will start, I have the system, the same as before, equation 1, equation 2, equation 3, the three equations. They are only coefficients, x under x and under y, z under z, and independent terms, operations. We are going to do 0 under this line, then 1, 0 here, 1, 0 here, and 1, 0 here, this 2. Well, 2 minus 2, well, equation 2 minus 2 times the equation 1, and equation 3 minus the equation 1, I will already give those 2 zeros. As you can see, I have only 2 zeros. Doing these operations and modifying the numbers appropriately, well, the next operation, minus 7 and minus 7. Well, simply if I subtract these two, it will give me a 0 here, which is what I am looking for. Well, let's subtract them. E3 minus 2, equation 3 minus equation 2. I already have the 0 here. I already have, therefore, all the zeros under this diagonal, 0, 0, and 0. So now we have to transform it into a system. New equation 1, new equation 2, and new equation 3. What happens when we transform it into a system? I have x plus 5, y minus z equals 5, minus 7, y minus 2z equals 9. And here, well, this is only the z. But it would be 0 by x plus 0 by y plus 0 by z equals 6. That is 0 equals minus 6. That is impossible. There is no value of x and y of z that multiplied by 0 makes me say that 0 is equal to 6. That is why we say that the system is an inconsistent system that does not have a solution. It does not have a solution because this is not going to be fulfilled, never. And since the two systems are equivalent, then this original system does not have a solution either. Well, this is what happens when the system is inconsistent, that an equation comes out that is not going to be fulfilled, never. Well, with this we have seen, we have remembered a little what are the linear equation systems, and we have seen how they are resolved using the Gauss method.